Welcome back. Do you remember that little contraption here? That's here on the Breakout board, an Allegro A1334 Hall effect angle sensor or rotary position sensor. And here we have a little magnet on a wheel that can spin. And the whole setup measured, of course, the angular position of the wheel, that is the magnet. It was connected via a 3.3 volt SPI interface to that 5 volt little Arduino Nano here. All these voltage dividers here on the Breakout board. Made 3 videos in total, I think, about the whole setup and how these things work, what are the drawbacks, what are the advantages, etc. Card here to the first video, and I think at least 3 more links in the description. Anyway, there was a problem. The A1334 is obsolete, so I bought up some old new stock, or well, new but obsolete part stock. But now the A1335 Hall effect angle sensor from Allegro is available again, at least at my distributor, so I bought some. So this is obviously the successor to the A1334, and it can do a lot more. It has some internal processing stuff, and it not only has an SPI interface but also an I2C interface, and in addition a SEND interface. That stands for single edge nibble transmission, and that's a single wire serial interface from the automotive industry. I just mentioned that once here because I'm not really interested in that one. Anyway, the goal of this video is to get that thing up and running with the I2C interface. Enjoy! As always, let's first have a look into the datasheet. So obviously I have here the 14-pin TS subversion that contains a single die. We have a look at the details in a second. But there's also a 20-pin version available that contains 2 independent but identical dies. Obviously to provide redundancy in critical applications. Let's have a look at a single die. And I highlighted green here everything that you also find in an A1334. So of course we have here our voltage supply with the internal 3.3 volt regulator. We have that multi-segment circular vertical Hall element. I explained how that works in detail in the A334 video. So rewatch them if you want to know how that thingy works. We have an analog front end and an ADC, of course, and we have some diagnostics. We have an EEPROM for storing some configuration data, and we have an SPI interface. In addition, the A1335 has also an I2C interface, which we will be using, and that automotive SEND interface. Now, the biggest addition here compared to the A1334 is a 32-bit microprocessor that can do a lot of stuff, including providing you with an industry-leading linearization. And I also talked in the A1334 videos about linearization and how I don't want to do that with the A1334, but will wait until I get the A1335 to do that. And we will do that not in this video, but in one of the following. Just for comparison purposes, the functional block diagrams of the A1334 and the 1335 side by side. As mentioned, the green stuff is exactly identical, and we have these 2 new interfaces here in the 1335, and the digital processing in the 1334, probably some 8-bit stuff and bit shifting and such, is being replaced based in the 1335 with a real 32-bit microprocessor core. By the way, the 1334 is also, or was also available with 2 dies in one 24-pin TS-sub case. Moving on to the typical application circuits, and we're mostly interested here in that I2C configuration. Anyway, you have of course a VCC pin for a 5-volt supply that has to be decoupled, and you have a bypass pin that gives you access to the internal 3.3 volt rail that has also to be decoupled, and you have a whole bunch of analog ground and digital ground pins that have to go to ground. Now, most important is the interface select pin. If you bind that to the digital ground, then you get an I2C interface. If you bind that to the internal 3.3 volt rail, then you get an SPI interface. If you select the I2C interface, you get a slave clock and a slave data pin here. Both have to be pulled up by typically 1 kilo ohm resistors to a 3.3 volt rail. Please note, these interfaces here, SPI and I2C, are both 3.3 volt. They are not 5 volt tolerant, even if the main supply voltage of that chip is 5 volt. Then you have here the slave address 0 and slave address 1 pins. Depending on how you connect them, so either to ground or to the internal 3.3 volt rail, you can set the 2 least significant bits of the slave address of the device either to 1, that is connected to 3.3 volt here, or to 0, that is connected to ground. We will talk about that 1 kilo ohm value for the pull-up resistors a little bit more later on. Anyway, if you select the SPI interface, you get a chip select, a slave clock, a master out slave in, and a master in slave out pin. Please note, these pins are physically identical. So depending on the interface you are selecting, they have a different function. Just to be complete, here's the diagram for the send interface. So I select goes to ground, and so does S-clock and MISO respectively. Slave data and slave clock, and that together activates the send interface here, which is a dedicated pin on the package. And using the slave address 0 and slave address 1 pins, you can also influence somehow the address of the chip. And here's the pin out of the 14-pin package that I'm using. So on the right side here we have a digital ground, then our 4 multifunction pins, then the send pin, we're not using that, and the interface select pin. That should be also connected to ground for I2C operation. And on the left side we have a lot of digital and analog ground pins and 2 not connected pins, which should also be connected to ground to improve ESD performance. So yeah, green should all go to ground. And then we have the bypass pin for access to the internal 3.3 volt rail and the VCC pin. Please note that almost all pins we need for I2C operation are located on the right side for the chip. On the left side we only need to access the bypass pin and the VCC pin, and of course ground in general. In addition, we don't need the send pin. We can let that dangle. This will become important when we try to come up with a layout for these TS-sub 14 breakout boards. One last tidbit from the datasheet, then we're done. So in the operating characteristics, we find that line about the SDA and SCL bus pull-up resistor, which says it has a typical value of 1 kilo ohm. That's the value we also saw in the circuit diagrams for I2C operation. There's no other information given in the datasheet for these pull-up resistors. There is also no maximum sync current given for the SDA pin. So we should keep as close as possible to that 1 kilo ohm value for our pull-up resistors. So I want to solder these little guys onto these breakout boards. And the breakout boards should make all necessary connections between the pins for I2C operation and also hold the two decoupling capacitors. At one side I want to have a pin header that gives me access in the end to the I2C bus, VCC and ground. Let's start with the circuit diagrams for those breakout boards. And I have here the circuit for a breakout board with the slave's LSBs set to 0, 0. That is the slave address 0 and slave address 1 pin are both bound to ground. And I get ground here via my pin header. And I loop that here to the left side of the chip where I connect all pins that need to be ground to ground, and that loop goes to the right again where we connect I select to ground, which needs to be ground for I2C operations, and then we go back to our pin header where we have a second ground pin. Please note that forms, a ground loop. You should avoid that in general, but in this case I don't think it won't pose a problem. Naturally, I have here the slave clock and slave data available on my pin header, and I also have the slave address 0 and 1 available of the pin header, but they're just there. They're connected to ground, not really usable. Since sand is just dangling in the wind here and not used, I can use that pin on the pin header to somehow route VCC to the back of the chip, the left side to the VCC pin. And I also have here on the left side the decoupling capacitors for the 3.3 volt rail there at the bypass pin to ground and at the VCC pin also to ground, of course. I have here a second circuit for the slave addresses LSB set to 0, 1. The only difference to the first circuit is that the slave address 0 pin must be somehow connected to the bypass pin, the internal 3.3 volt rail. Now for the layout. Please keep in mind that these are double-sided breakout boards. On the back there are larger pads for SOIC 14 packages. And the through holes for the pin headers are of course connected through between the back side and the front side. There won't be much happening on the front side of those breakout boards. I just want to have the chip there and nothing else, so a really clean look. One modification I do have to make here is I somehow have to break the connection between that pin here, that's our unused send interface pin, and that through hole, because I plan to use that through hole to feed in my VCC. The backside is a totally different story. Please note, this is mirrored now. So we're really looking at the backside of the breakout boards. Let's start with all the ground connections. So here's pin 1 of my pin header, that's ground, and that is naturally going here through the connections to that digital ground pad here, and then to the slave address 0 and slave address 1. I have to jumper that somehow here, and that gives us slave addresses least significant bits of 0, 0. Then I have to jumper here across the breakout board to that next digital ground pin, and then I simply connect from that side all the other ground pins and not connected pins. So that digital ground, that not connected, and another analog ground. And I jumper again here over the pads on the back side to my I interface select pin, because that also has to be connected to ground, and we go back here to the other ground pin on my pin header. VCC goes from that pin of my pin header to that pad. And remember, we disconnected that pad that was the send pad on the front side. And then it jumps over here on the breakout board to the actual VCC pad. And here at the back side, I simply put a decoupling capacitor across from that line to ground. There's a second decoupling capacitor here for the bypass pad, so the internal 3.3 volt rail, of course connected to the ground here on the other side. The slave clock and slave data pads here naturally fan out to my pin header. So do the slave address 0 and slave address 1 pads here, but as mentioned before, I won't be using them. The layout for slave addresses least significant bits set to 0, 1 only slightly differs at the back side. So my slave address 0 pad here is no longer connected to ground, but I also jumper over here the pads to the bypass pad, so the internal 3.3 volt rail, while a slave address 1 is still connected to ground, but I get the ground here from the other side. That's one of the digital ground pads. And here are the finished products, and I won't torture you with a long SMD soldering sequence this time. If you want to see me SMD soldering, there's a card here and a link in the description. Anyway, as mentioned, I only have the chips themselves here on the front side, and there are two tiny drill holes here and here, severing the connection between the send interface pad, the second pad, and the second pin of my pin header here, because that's, remember, is VCC. On the back sides, we have here on the right all those ground connections and the decoupling capacitors. Yeah, these loops are not very nice. That was my first try. And we jumper that ground pin here to the back via the pads, and we do the same here for the top ground pin that also goes to the back, and we jumper over the VCC pin using the unused send interface pad to the VCC pad here at the back. The only difference between the two versions are the connections of the slave address 0 and slave address 1 pads, which are here connected also to ground, and here the slave address 1 pad is connected via another jumper here to the back to the bypass pin pad, so the internal 3.3 volt rail, while slave address 1 is also connected to ground, but this time using a ground pad here on the right. We still need a circuit for breakout board, and this time I won't be using the Arduino Nano Every, but the classic Arduino Nano version 3. The USB connector is here just for orientation. Of course, we have to bugger out our slave clock line and slave data line somehow to our breakout boards, and these will be pulled up by resistors to the 3.3 volt rail of the Arduino Nano. Remember, that's a 3.3 volt I2C bus, and it's completely okay to do that for most applications. There might be some leakage currents here from the 5 volt rail and some high value pull-up resistors also connected to the 5 volt rail, but as long as these resistors are sufficiently small, that should work in most situations. Anyways, we also need a ground connection to our breakout boards and the 5 volt rail. The only question left is, what value should we use for these pull-up resistors? Should we use the 1 kilo ohm from the A1335 datasheet or something else? To answer that question, we have a look into the AT-MEGA328P datasheet that is used on the classic Arduino Nano version 3. And there we find on the 2-wire serial bus requirements, figure 28-7, this nice formula here for the minimum resistor value. So VCC, that's in our case 3.3 volts, not 5 volts, minus 0.4 volts, volt divided by 3 milliamps. And if you put that into a calculator, you get 967 ohms as minimum pull-up value. And yeah, so we could in theory use 1K. However, I'm using those cheapo resistors with a 5% tolerance, and that could in theory go down to 950 ohms and yeah, breaking that minimum limit. So I will be using 1.1K resistors. And that's how the whole thing looks on the breadboard. I have here my two pull-up resistors connected on one side to the 3.3 volt rail and on the other side to the slave data and slave clock line. Both lines bugger off here to the breakout boards, and so does the 5 volt rail and the ground rail. I placed the breakout boards here at the edges of the breadboard, and I removed the power rails so the chips are easily accessible with a magnet or some other jig. Please note the interconnections between the two breakout boards. They are of course diagonally here in the middle because yeah, the breakout boards are turned 180 degrees to each other, so the sequence of pins is exactly reversed between the two. And in addition, I created another evil ground loop. Wouldn't it be great if there were already Arduino libraries available for the A1335? And indeed, there are. I found two. That is, well, 1.5. You'll see. First off, we have Scrunch News Allegro A1335 sensor library. It's a rudimentary thing. I mean, that's the documentation for the library, and it consists of two files, a .h and a .cpp. There are two forks, but these are really just copies that some people made of that library. I don't know why. Let's have a look at the header file then, shall we? So, and here you find the real name of the guy, so Florian von Bertrap. It's a German name. I think it was also in the description, wasn't it? Yes, it was. Anyways, you have here two helper classes for handling the 16-bit registers, respectively 32-bit registers of that chip. Remember, it has a 32-bit CPU core. Here's our main class with a constructor, no parameters here, and then a start method that gets the I2C address. Why that is 16 bits, I don't know. Then you have here a getAddress method, yeah, for the I2C address, and a getProcessState, which will return booting, idle, running, and whatnot. And then you have here a getOutputDataRate, which returns a byte. Interestingly, we have here also a readOutputDataRate, which also returns a byte. I think they do basically the same. You have a read angle in degrees, and you have a read angle in raw data format, so the binary format the chip is using. Why that is a double for an Arduino library, I don't know. You have a read temperature. Yes, the A1335 has also a temperature sensor inside it for temperature compensation. You get also the raw value, and you get the magnetic field strength of the field you are measuring the rotation of. And that either in Tesla or the raw binary value. You can, we already saw that, read the output data rate, but you can also set it, of course. And you can normal write the 16-bit integer registers and normal read those registers. And you have here an extended write method for the 32-bit registers and a related extended read, of course. We will talk about the registers of the chip much more in details videos, okay? Anyways, here is Rob Roy's A1335 _ utils, and I called that which is not very nice, half a library. That's because it's not really a library. That thing is basically the repository of all related stuff to our angle sensor boards on Confluence. So yeah, if you want to see also some PCB layouts and stuff, that's a nice thing to look into. Anyways, I called it only half a library, because if we go in here and search for the code, there is no really a CPP file. There is a rotary encoder library, So yeah, there's nothing here that you can really use out of the box, but I think there might be some code in here that you can copy and paste into your own projects. That's why I mentioned that thing. And besides, maybe you want to make your own breakout board and not create these awful contraptions I have. Now, all that's left to do is to write a little sketch, which I've done here, to test things out and see if everything is really working. And I will using that Scrunch new library here. I put links to the libraries also into the description, and also a link to my Google Drive where you can find exactly this sketch here. Anyway, so we're using that A1335 library, and I have two breakout boards. So I have A1335 left and right address, and the left address is both least significant bits being 0, so that's 0C hexadecimal, and the right breakout board has the least significant bit set to 1. So we are here at hexadecimal 0D. Then I have two instances of objects from that library, and I have here also a byte arrow left and arrow right. We will see in a moment how I use them. And then in my setup, nothing much happens. I initialize my serial port so we can see something on the serial plotter. I will show it on the serial plotter. We wait until the serial port is ready, and then we do a wire begin. Yeah, I don't like libraries that implicitly use these global Arduino objects and do not pass them via the constructor. This is not done by the library. You just have to know it. We saw there is no documentation. So, wire begin. Then I do a A1335 left start with the left address, and that little method returns the wire end transmission error if some was returned by wire end transmission. And I store that in error left, and if there was an error, so I get a value not equal 0, I print out that error. And I do the same for my right sensor here. And finally, in the loop, I check if there was an error. So if either error left or error right is not equal null, and then I jump out of the loop again. Otherwise, I do a delay 500 milliseconds, and then I print out the left angle and the right angle in a format suitable for the serial plotter. Now, maybe we can turn that down here to, I don't know, 200 milliseconds. Yeah, just in case. And yeah, let's see if everything works. I've modified the jig a little bit so it would fit the breadboard here. Well, kind of fit it. And the principle is still the same. So we have here the magnet. Let me zoom down. On the cogwheel, and on the other side our sensor, and that should give us a real nice signal. Of course, since I have only currently one cogwheel with one magnet, we will first test the left breakout board and then the right breakout board. And that's how the whole thing looks like on the serial plotter. And the blue line, that is my sensor that we are actually testing right now, so near to the magnet. And the red line, that's the right breakout board with a sensor and no magnet. And you see this is basically just noise, some random value. I would expect here something like, yeah, not a number returned from the function, but as I said, the library is very rudimentary, but obviously it works. So if I turn now the wheel, and here at the top we are at 300, almost 360 degrees. So if I turn the wheel, we go down to 0 degrees and then up to 360 degrees again. And you see the right sensor is also influenced a little bit, but yeah, it's really just random values. Down to 0 again and up to 360 and 0 again. Anyways, let's try the other breakout board, the right one. So I turned the jig around, so now the right breakout board is here at the magnet, and as you can see, now the red line is almost constant here. There's absolutely or almost no noise, and now the blue line, so our left sensor, is producing some random values. Not quite random, but quite noisy. Too far away from the magnet for real measurements. I'm sure the chip is giving error messages, and yeah, a real library would have to take that into account. Anyways, if I turn this now, we go, okay, the other way around, of course, because I turned it around. We go down to 0 degrees, and then we are up at 360. And we are going down to 0 degrees again and back up to 360 and so on. Nice! Now that we've covered the basics, so we made some breakout boards here for the A1335, and we found a, well, library, a rudimentary library, but it's working and everything is up and running. What are the next steps? First of all, I need a better jig here, but this will probably be a standalone video, a new kind of video, a LEGO Technic build. We'll see. And then we have to dive into the details of the A1335, because I'm not going to continue to use that library. I need something better there. So we'll have our work cut out for us. Till next time, bye.